Hey, how's it going, all? I just want to do a fairly quick talk, but this is a test that a group of us, brainstormed earlier after Jose's hangout. He left, the stream running for us, and so we had a group of flat earthers and ball earthers and kind of the usual suspects, and we came up with this test. It was mostly inspired by using GPS, which I'm just a big fan of because it's ubiquitous. It's people have access to it. It's repeatable and all that kind of stuff. And so it's a fairly straightforward concept. So I'm going to just put this out there just to get the concept out for people and then, solicit feedback on, what people think and any ways it could be improved and all that kind of stuff. And so I call it assessing Earth shape via high-end GPS, lasers, and a boat. So the procedure for the test is actually fairly simple. First step, which is the most crucial step, is to establish a cube of data points using GPS. And so I'll walk people through that with pictures and that type of thing. But really the entire test sort of hinges upon this step being accurate and this cube being able to be extrapolated fairly. And so once that's done, the next step is then a fairly turnkey sort of operation. Time consuming, but fairly turnkey. You take a number of samples directly on a water body with a boat that's enabled with preferably that same GPS unit that was used in step one. And whenever, for the purpose of this talk, just whenever I talk about GPS, I'm not talking about like the GPS on an iPhone. I'm talking about a high-end unit. And so there's certain cost implications, but just for now, assume that it's a fairly precise, GPS unit, and that GPS unit would need to be on a boat, and then so you go across a body of water, preferably the same one, but even a different one is fine. It's just the issue of getting the boat to those different locations is sometimes cost restrictive and time limited and all that. So, but let's just assume we have access to like one of the Great Lakes or something like that. We would need a boat enabled with this GPS unit to take samples along the surface. And then basically you just plot the points in step 2 onto the grid created in step 1. And so to assess what the shape of at least that water body is. And so that's sort of the foundation, and I'm kind of walk through these with pictures and let's go. So I'm just using these first 2 slides just to, this is from a talk that I did with George on, again, Jose's hangout, and kind of really the fundamental concept here behind this whole test is that GPS fundamentally is just a position in 3-dimensional space. It's latitude, longitude, and elevation, but more fundamentally, it's just 3 numbers. It's just wherever you move your phone or a GPS unit, it gives the person reading it 3 numbers back. That's really all it is. You can call it latitude, longitude, and elevation. You could call it XYZ. You can call it ABC, DEF. It doesn't matter. You can call it anything. It's 3 numbers that give a recording feedback of where that unit is in 3-dimensional space. The trick here is that it's not unique because you can still move your phone or unit a little bit and get the same reading. So that's why I have these grids here, because only when you move a GPS unit an appreciable distance will you be able to get a new reading. And so that's why in this picture below, these iPhones are not sitting right next to each other. There is a certain amount of distance these units will have to travel in order to get a unique reading. And so, again, more expensive GPS equipment, you would only need to move it maybe like a couple centimeters to get a new reading. And then it will, honor that new position with a unique set of 3 numbers. And we'll call that, a GPS coordinate. But fundamentally, like I said, it's just 3 numbers. And so basically establishing this type of grid using GPS along straight lines, to me, is a very, very powerful way to sort of use it to establish a coordinate system. And so this would be our grid. We could now, and I'll, again, use pictures to kind of give at least my first thought as to how we would set this up. But again, fundamentally, it's just using a GPS unit, moving it along a predictable path, and then creating a grid. And the nice thing about this type of thing is that there is some sort of built-in accountability, built-in checking, verification, in that, let's say those 9 data points on the left we've established with actual, moving the unit to those different places. In this case, I just put an iPhone just as a cartoon, as a picture. The nice thing about this is we should then be able to make predictions about this grid and say, okay, if we're going along this same straight path, a certain number of a fixed distance, we should get this reading based on the extrapolation of those 9 points. And we can sort of keep ourselves honest, or whoever builds this grid keep themselves accountable that they're doing it correctly. And then that's again the nice thing about this. Obviously, this test that I'm going to propose, you'll see, requires this grid to be extrapolated much further. But again, if we especially if we're doing this kind of in an open area where GPS can kind of not have these multipath type things and produce a reliable result and all that, there's no reason to think that those 9 points are not stable. And then let's say we check a few of them in the distance, and then it works, it holds, and then we can have some comfort that it would hold miles and miles down the road, so to speak, or down the water in this case. So that's sort of the idea, establishing what I call a neutral and local coordinate system. And so essentially what we're doing is not just doing it in 2 dimensions, we're extending this concept to 3D and then using high-end GPS. So the way it would start is you'd need to have, I'm recommending lasers. It could really be anything that's straight, but here let's just think of lasers, I guess, for now. It's shooting in those 2 directions, and then those blue dots represent the granularity of the GPS unit. And so each of those blue dots represents a unique number that GPS unit can output along straight lines. That's the most important thing. Those lines have to be straight in the X and the Y. And then so, again, each of those blue points represents a position in 3-dimensional space assigned a unique set of 3 numbers. Let's just put it generally like that. There are 3 numbers that tell me that which of those blue dots I'm sitting on. And so you basically do this. Now we're going, into the page, so to speak. We'll consider that the Z direction for now. So you just move these lasers along this cube, and then you produce a new set of 9 numbers, again, with a unique set of coordinates, 3 numbers. And you just keep doing this. And then so the distance between this set of grid and this one into the page, going into the screen, depends again on the GPS accuracy. But let's say this unit is the same in the X and the Y. Those distances would have the same, the gap between those blue dots in this picture would be the same into the page. And so basically, after you do this, for enough points, I would recommend extrapolating some out, 100 meters down, 200 meters down, and verifying that, along that line, this local coordinate is able to be extrapolated and predicts those coordinates further down correctly. Do at least a couple of those samples. And so this is our sort of mesh. This is our grid. And it's all straight lines, and each data point, each intersecting line has a unique GPS coordinate. And so this grid is going to be very, very important once after we take some samples. So that's our grid. Now all we have to do, and I don't say as if it's like super easy, but the sort of easier part, the more turnkey thing, is we would need that GPS unit, being able to be loaded on a boat, and have that boat go to, a vast enough set of points on a water body to collect samples. And so here I have these yellow stars that let's say it can go to. I just kind of drew it along the shore, not for any particular reason, but wherever it can be. And again, the more points, the better. And they could be some clustered, some further away. Just really the more kind of random it is, sort of better. And, obviously the boat will be rocking up and down with waves potentially. But, as the boat sits there at, it will take an average. You don't want to take the highest or the lowest value. In this case, you want to take the one that it truly is when it's, perfectly settled and calm. And so it may need to sit there for a couple minutes, but, you just if you go to enough points and you let it settle and let it average out with enough time, in this case, you're averaging over time, you could get a fairly stable, coordinate at all these yellow points. And then, so again, the larger collection of yellow stars you build, the more and more accurate that our assessment can be of the shape of that water body. And so now we have these yellow points, and all we do now is we just need to map those onto the grid that was created in step 1. And so those yellow points will now effectively be outside of the GPS coordinate system, because now we're mapping them onto this cube. And it sort of kind of neutralizes the effect of being in a GPS coordinate system, because now they're just mapped along these straight lines. And so if the Earth is indeed flat, or that water body is fairly flat, we would see that when those points are projected onto this cube. And if it's not, we would see quite a bit of drop really on all sides of these points. And again, the further out that we're able to take these data points, the less likely we'll have an ambiguous result. So, it's to me, it's fairly elegant. I think just from the initial thoughts that some of the Ball Earth people have, it's doable. It's not like, we don't need some, material science advancement or some major sort of game-changing technology to do this. This is all stuff that people have done to do things, to build buildings, stadiums, do surveying and all that kind of stuff. And GPS, again, the nice thing about it is that it's really hard to argue. It's like, if someone says that this is a straight line, which lasers are fairly, reliable to create them, at least on a local level. Certainly they're able to be straight in the granularity of these high-end GPS units, which apparently, like, you move a few centimeters, you can get a new reading. So on that scale, lasers are very, very straight. And so, you can shoot a laser, you can move along its light, its path, and, verify that this cube has correct GPS coordinates. And so it's very reproducible, very repeatable. There's not a lot of sort of sleight of hand that can happen here. And, that once that coordinate system's established, the main assumption in this whole test at that point forward will be, does the extrapolation hold, which is fair. We would have to be aware of any kind of errors getting magnified in a grid that's being extrapolated very, very far, which is fine. We would need to, again, try this once or twice. And the errors, and then taking readings on the boat, just, again, with the water not being calm and all that. But again, I think like scoping out a water body or a particular day that is calm would help a lot. And so the cool thing again about this is that, let's say the test is done and then there's a result. This kind of similar procedure could be done elsewhere. And hopefully, if this GPS equipment is very, very expensive, hopefully it can be rented for a day or two. And a lot of people have access to a boat. So, then it's just a matter of, time and taking these points. And the cool thing about this is you don't really need to go to specific points in the water. You just go to as many as you can, random ones, and just literally write those numbers down, and or create an Excel table or whatever, and create a log. And the more points, the better, because the outliers will be obvious. Let's say, the GPS just hiccups and produces some garbage number that'll be very obvious on the plot. If you see one point, or a few points, kind of spurious points all over the place that don't support or round Earth or a flat Earth, we know to sort of dismiss those. But, it's just really as many and as random points as you can gather, and stable points in terms of just allowing the boat to kind of settle in on a number. And then, that unit is just slightly above the water and fairly consistent as it sails around. So, it's, I guess technically that difference between where the unit is and the water body, you could account for that. But, let's say that the boat is in a similar orientation where it's taking each of those yellow points, that coordinate is fairly reflective of the water body beneath it. So that's pretty much it. I just put that out there, and I'll leave comments open if people want to leave feedback. Anything that's not constructive or just this is dumb or some sort of hand wavy thing like that, I'll delete, only because there's been some sort of understanding on both sides that it's at least possible. It's not, again, space age kind of stuff. But if anybody has expertise or has done something like this, and again, to me, setting up the grid is the most amount of work, and then those yellow points in the boat, people can do kind of at any time afterwards. So it's kind of a two-step thing, and ideally they could be done on the same day, just again to sort of minimize the amount of errors that could potentially happen with using a GPS, on different days and, getting slightly different readings. But, who knows? Again, with very, very accurate GPS, one would think that it's not, dependent on the day, and atmospherics and stuff like that. So, all right. Hope everyone's doing well. Bye.